the cleanest rooms in the world. It is a room in which integrated circuits are fabricated and tested for possible use in the Bell system. Special clothing is worn to protect the working environment. A single speck of dust from street clothing can ruin a microelectronic circuit. Sodium from the skin is an instant contaminant. Dust particles are sucked into holes in the floor by a central filtering system. Fresh air is constantly circulated. To protect photosensitive materials, certain areas in the room are bathed in yellow light. The dust level in a modern hospital operating room is about 10,000 particles per cubic foot. In this room, there are fewer than 100 particles per cubic foot.
This is the Integrated Circuit Processing Laboratory at Bell Laboratories in Murray Hill. In this laboratory, we do work on the development of new integrated circuit processes and new integrated circuit designs for equipment destined for use in the Bell system.
A large-scale integrated circuit may contain tens of thousands of circuit elements within a chip of material only a few hundredths of an inch thick and perhaps a 20th of a square inch in area. The communications industry is one of the largest users of such advanced electronics. Making experimental microelectronic circuits is an intricate process. It begins when an ingot of pure silicon is sliced into wafers by a thin, high-speed diamond saw. The wafers are about 1/50th of an inch thick and 3 inches in diameter. About 100 complex integrated circuits can be formed on this wafer. Silicon is an ideal material for microelectronic circuits. It has excellent electrical capabilities. This most plentiful element is extracted from sand. There can be no defects, scratches, or chemical impurities on the finished surface, so the wafers are scrubbed of all particles of dirt and cleaned in a mixture of acids. The operator must wear protective clothing, for the acid is strong enough to eat through the skin. After the wafers are cleaned in acid, they are rinsed in ultra-pure water. Then they are spun dry at high speed and are now ready for oxidation. Oxidation, or the growth of silicon dioxide on the surface of the wafer, takes place in ovens heated to more than 1,000 degrees centigrade. The temperature is controlled to an accuracy of better than 1 degree. A computer supervises the entire procedure. When the oxidized wafers have cooled, they are coated with a photosensitive material. Spinning the wafer spreads the liquid emulsion evenly over the surface. Now the wafer is ready for selective exposure. The now photosensitive wafers are exposed through a glass mask that contains circuit patterns. The mask was made by a computer-controlled electron beam in a process that is accurate to tolerances within 10 millionths of an inch. The reference mark is aligned very carefully, leaving the unmasked surface areas open to exposure, working like a stencil. A part of the integrated circuit pattern is printed into the photosensitive material on the oxide surface. The patterns in this case are etched in the oxide by a dry vacuum process. The areas not covered by the photosensitive material are removed, leaving the pattern raised on the surface. The result now becomes visible. The wafers are inspected for quality of etching, proper exposure, and alignment. From here, the wafers go into a machine that strips them of their photosensitive material, leaving the circuit patterns intact. Next, in order to change the electrical properties of the silicon within the area of the etched oxide, the silicon wafers are bombarded with electrically charged atoms, called ions. The wafers are heated again to about 1100 degrees centigrade to diffuse the atoms deeper into the surface layer. These cleaning, oxidation, patterning, and diffusion steps are repeated several times in the process. The patterned sections form the transistors and other elements in the integrated circuit. Now all of these elements must be interconnected. Under vacuum, aluminum is vaporized and deposited on the wafer. The patterning process then defines the conductors that connect the circuit elements. The completed circuit is then tested. These chips that pass the test perform an electronic function similar to those of a large computer. The wafers are sawed by a diamond blade into chips 1/20th the size of a postage stamp. The completed circuits must undergo two last operations, bonding and packaging. They are bonded with epoxy in a protective housing that has connections with the outside world. The circuits are connected to the electrodes leading out of the package by fine gold wires, 1/3 the thickness of human hair. Microelectronic circuits help provide faster, less costly, more versatile, and more reliable service than earlier telephone equipment. They allow Bell System communications equipment to measure, monitor, and maintain itself, and at the same time, to meet the increasing demand for new and improved telecommunications services.